welcome back to this course on analog electronic circuits. We are almost to the verge of second week of this course, and today's topic of discussion is linearization of a nonlinear circuit, which contains MOSFET. So, to simplify the analysis, we are considering example having only one MOSFET transistor in the circuit. So, let us see what is the where we are in the flow. In our overall flow, in the second week discussion, we are basically linearization of input to output transfer characteristic of nonlinear circuit containing BJT or MOS. And in the previous module, we already have seen linearization of input to output transfer characteristic of circuit containing BJT. Today, it will be similar kind of discussion, but then instead of BJT, we are focusing on MOS transistor. And then similar to the BJT circuit, we will also be having a notion called small signal equivalent circuit, and from that we will see that that is a notion of small signal model of MOSFET transistor. So, and then we will see that how the small signal model helps us to speed up the analysis and helps us to find the gain of the circuit. So, that is where we are. So, the concept it will be covered today, it is linearization of nonlinear circuit containing MOS transistor, notion of small signal equivalent circuit, and then small signal model of MOSFET, particularly in MOSFET, and then we will cover how the small signal model of MOS transistor can be used to solve numerical problem. So, to come to the example, so here we do have the running example. Here we do have the common source amplifier, and at the gate we do have the voltage we are applying, and at the drain we are applying supply voltage through R d, and then we are observing the output at the drain, namely drain voltage there, which is incidentally the output voltage. And what we are going to do, that we like to change the input here, namely the gate voltage V g, and we like to observe the corresponding effect on the I d s and on the V d or V d s. So, if we vary the gate voltage V g, incidentally that we are changing V g s of the transistor, and we can see what is the corresponding effect at the I d s and the V d s, which is the output of the circuit. And this is the information, it is known to us. If the transistor it is in saturation region, expression of this I d s in terms of V g s and V d s is given here. So, we do have transconductance parameter K and W by L aspect ratio of the transistor, V g s minus V t h the threshold voltage of the device square, and 1 plus lambda into V d s. And to keep the device in saturation, V d s should be higher than V g s minus V t h. This is also denoted as V d sat. Now, you might have noted that I am using slightly different notation for each of these parameter. Say for example, I d s capital I small d s, which means that this I d s is subjected to change with time, and so likewise V d s capital V small d s and then V g s also. So, if I vary this V g or V g s, we like to see what will be the variation there. And if I say this is the input, so if I say that this is the input and if I say that this is the corresponding output, we may say this is also output, but let you consider this is the output. Then input to output variation, what is known as input to output transfer characteristic. So, we are expecting this transfer characteristic, it will be highly nonlinear because the device it is nonlinear. And then we will be talking about how the nonlinear characteristic curve it will be getting linearized. Okay. So, let me use a new slide for that to go for further discussion. Yes. So, here we do have the common source amplifier, where we are changing this V g s and we are observing the voltage at the drain. As I said, we do have the V d d. Now, here the known information, as I said before, in saturation region, it may be typically it is well approximated by considering this lambda is very small, namely lambda into V d s it is much smaller than 1. So, we can ignore this factor and hence we can say that I d s is approximately defined by only this part. Okay. So, which is indicating that the I d s current, here, though it is function of V g s and V d s, but we do approximate that this is function of V g s only. Whenever it requires, we will be considering this factor, namely the dependency of the I d s on V d s. But for the time being, let me assume that I d s is predominantly defined by V g s and its expression is given here. Okay. So, how do we find the transfer characteristic? So, first of all, if we vary the V g s or V g, we know that this I d s it will change, and the dependency here it is square law. And then to find the output voltage. So, this is either you say this is V g or V g s, and to find the corresponding output, what we do? We consider the load line as well. So, the load line in this case it is defined by this straight line having a slope of minus 1 by r d, and this point is V d d as we have discussed in our previous modules, and this point it is V d d by r d, and wherever it intersects that gives us the okay. So, okay. So, let me I have committed a mistake. So, let me come back to this point. So, first thing is that we do have the I d s versus V g s. So, that is the square law, and then to find the output voltage, what we have to do? We need to plot the I d s versus the output voltage. So, for a given value of V g s, so the current it is hardly it depends on the V d s. So, we may say that the device characteristic, namely I d s versus V d s, it is constant here in the saturation. And then if you draw the load line defined by this R d and the supply voltage. So, this is one end of the load line VDD, and then the other end of the load line it is VDD divided by RD. So, this defines the output voltage or the VDS. So, the VDS here it is given here. Now, as we have discussed before, if we vary the VGS with respect to some point, then what we are expecting that the device characteristic it goes up and or it may come down, and as a result the intersection point it is changing, and that gives us the variation in VDS with respect to variation in VGS. So, whatever we see here, if we plot the variation in say VDS with respect to variation in VGS. So, then what we will be getting here it is in the middle portion it is fairly linear, but then if you decrease this VGS say maybe towards the VTH. So, it is expected that it will be having a highly nonlinear part. Then we do have beyond some point, if I increase this VGS, then it may be the device characteristic it may be approaching towards VDD by RD, and there we will be having another nonlinear part which will be the other way. So, you may say that this nonlinear part it is coming due to device entering into triode region. On the other hand, this nonlinear part, or rather here it is coming due to device entering into the cutoff region. So, whatever the overall transfer characteristic we are getting here, it is as I said that because of the device characteristic which is fairly nonlinear, we do have nonlinear input to output transfer characteristic. So, this nonlinear input to output transfer characteristic we need to linearize. So, we have seen that this portion middle portion of the characteristic curve it is fairly linear, and whenever you are talking about linearization, if we are keeping our linearization center around middle of this range, then the linearity range it will be bigger. So, whenever we are talking about linearization, probably we need to fix one point called quiescent point or Q point, and with respect to that Q point we may try to linearize, and whenever we are linearizing we can say that this Q point it is defined by the VGS, maybe V capital GS, and the corresponding output it is a V capital DS, and with respect to we may be having some variation. So, if we are having some variation here, the corresponding effect it is coming here, and in this plot input to output transfer characteristic we may say that if we change this VGS with respect to this Q point, here we will be seeing the corresponding effect coming here at the output. So, this after doing this linearization, we are assuming that this Q point or operating point it will be unchanged, it will be remaining fixed, only the VGS small portion it will be changing centering to this Q point. So, our the circuit now it will be having supply voltage having a fixed DC part and the time variant part. So, let us look into this circuit in different way, where at the input we are giving a DC voltage followed by one time varying component, and then we want to see what will be the corresponding effect coming at the IDS current and also at the VDS voltage. So, that is basically graphically when we are saying that nonlinear transfer characteristic curve we are linearizing. Here we are saying that we are changing the Vg with respect to a fixed DC voltage, and the variation here it is we are restricting, so that the effect coming here it will be fairly linear with respect to whatever the variation we are imposing on the gate voltage. So, let me start with new slide. Yeah, this is what exactly I was talking about. We do have the supply voltage. So, again this is the same common source amplifier or common source configuration. It is having at the gate we do have a DC voltage. So, this is the DC part which is defining the operating point, and on top of that along with that it is having the small signal part. So, you may say that this is AC part or time varying part. Though pictorially here we are showing it is sinusoidal, but it is not necessarily be sinusoidal. Only thing we want to say that its average should be 0. So, with progress of time the quiescent point or the DC point it remains unchanged, and it will be having impact on the IDS current. So, it may be having AC part, and of course, it will be having a DC part. So, likewise this output voltage it may be having a DC part called V capital out, and in addition to that it may be having small signal part, say small V out. So, if I see the current here, it is having, as I said, that it is having DC part denoted by capital I capital DS, and then it is also having a small signal part small I small ds. So, the total current flowing through drain to source of the transistor that can be obtained by considering the same equation. Only thing is that the VGS part we are splitting into two part, one is the DC part, another is the small signal part, rest of the things it is same. So, to know what kind of effect it is coming here, if we expand this equation, probably we can get the exact one, and also we can get what will be the corresponding linearization. So, if I expand this, so we do have k divided by 2 w by L as is, and then if we take this part VGS minus VTH part separate from this VGS, what we do have it is V capital GS minus VTH, and then plus small v GS. So, we do have square around that, but let you take this part separate and let you take this part out. So, what we have it is k divided by 2 w by L VGS minus VTH square. So, if I take this part out, what will be having here it is 1 plus VGS by V capital GS minus VTH square. Now, if I expand this part, what we are having is, let me write this part k divided by 2 w by L VGS minus VTH square 1 plus one plus 2 into VGS small VGS divided by capital VGS minus VTH into VGS plus we do have VGS square divided by capital VGS minus VTH square. So, now if I say that we are talking about linearization, which means that we are essentially dropping this second order term. So, if you make this is approximately 0, whatever the remaining term we do have here up to this point, that gives us the linearized transfer characteristic. So, if I say that if I multiply say 1 and this part, so that gives us the DC part. So, we may say that this gives the DC part, and after linearization if I multiply say this part with say this part, then multiplied by VGS. So, that gives us the AC part. So, we can say that the small signal part or the AC part IDS part, it will be K divided by 2, and this 2 and this 2 are getting cancelled. So, K W by L VGS minus VT. So, the square part it is getting eliminated because you do have VGS minus VTH multiplied this VGS. So, you can see that it is having the VGS part, and rest of the things are if you see it is unchanged. So, if I say that only small VGS part it is changing, so the corresponding change we are getting at in the current, it is the DC part the some factor here defined by the DC part, and then we do have the time varying part small VGS. In fact, this part it can be rewritten in different form. In fact, it is having 3 different forms. We do have say form A, form B, and then form C. All are same. Only thing is that if you see here in this form, this part it is defined by W by L and VGS minus VTH, whereas for this case it is in terms of IDS and VGS minus VTH without considering W by L. And then we do have the third combination, it is IDS and the aspect ratio W by L. So, depending on the situation we may take one of these forms, but everywhere we do have the VGS appearing. So, I should say whether this form or this form or this form, all the terms are essentially representing the same thing, namely transferring factor from VGS to IDS. Okay. So, so now what we are seeing here it is, so if you recall the nonlinear input output transfer characteristic. So, okay, I will be coming to this nonlinear transfer characteristic. So, let me go to the V out part. So, now we obtain the current part, and now we like to go to the final output voltage. So, you may keep this information in mind, and we will be making use of that. So, as I say that this is what we obtain, the expression of small IDS part in terms of VGS, and the expression of capital IDS we already know. So, let us see how do we find the corresponding output voltage. The expression of the output voltage, of course, it is we do. So, this is the output voltage which is VDD minus this IR drop. Now, the IR drop is basically we do have the RD multiplied by the total current, which is having the DC part as well as it is having the AC part. And from the previous discussion we already said that the expression of this the total current, which is given here. It is having the AC part, and then also it is having the DC part. And the DC part, its expression, it is given here. It depends on the voltage here, the DC voltage, and then the AC part, it is having this part, one of those three factors. In fact, this is the form, one of those three forms we have discussed. It is basically the form C. So, we can use any one of them, that is not important right now, but what we like to say that this is function of VGS. So, this IDS, it is having an expression like this, and this part it is having this expression. So, which means that if I multiply this R d with this capital IDS. So, what we are getting here, it is VDD. So, we are having this is capital VDD minus RD multiplied by capital IDS. So, this is the DC part, which is I should say that the DC part at the output, and then we do have the minus, I should say minus here, we do have minus R d into I d. So, this IDS, and then this IDS part, it is having this expression. So, we can write say this part particularly, this part in the form of minus R d square root of 2 IDS k W by L into VGS. So, as I said that we do have a this V out is having a DC part, V capital out. So, this part, it is basically the V capital out, and this part is the small signal part. So, in addition to that, we do have the time dependent part, or the part which is coming from this one. So, that is V out. So, that is nothing but this minus R d square root of so and so multiplied by the VGS part. So, that gives us the input to output transfer characteristic considering this time variable part. So, whenever we are talking about linearization, is basically we are keeping our focus on this relationship. Okay. So, what we are going to do now, it is we do have large signal transfer characteristic, which is fairly nonlinear, and then out of that we are keeping our focus here, we are talking about only this part, and whenever you are focusing on this part, the x axis and y axis are essentially the small signal part. So, we may say that whenever you are talking about this linearization, the x axis is small VGS and y axis is small VDS or V out. And whereas, if I consider the large signal transfer characteristic, the x axis, as we know that it was capital V small g s in this circuit, and then the output, it is capital V small out, which is same as VDS. Okay. So, whenever you are talking about linearization, is basically pulling out only this part, of the transfer characteristic. So, we are taking this part out here. So, in other words, we may say that linearization is basically getting a new kind of transfer characteristic. So, that is what we are saying, that whenever you are saying it is linearization of the transfer characteristic is with respect to one operating point, finding the small v I should say this is actually I want to say it is small v out versus small v g s. So, we are basically talking about the translating the large signal transfer characteristic. So, we do have v out with respect to v g s, which is incidentally v in, and as we said that it is having fairly nonlinear behavior, and out of that we are extracting the small signal part. And once you pull it out, and if we are observing the corresponding transfer characteristic, its x axis is small v g s, or you may say this is small v in, and then we do have the y axis, it is v out, which is actually small v d s, and this part it is coming here. So, if we extend, of course, it will be having nonlinear part. So, whenever we are getting this small signal transfer characteristic curve, it is basically we are getting new transfer the input output transfer characteristic curve, and this curve it may be obtained by some simplifying this circuit through an equivalent circuit, where of course, we can suppress the DC part or the quiescent part. Basically, this is the Q point or quiescent point. That part, if you map it here, that is equivalent of saying that if we drop this DC part and if you drop this DC part and also the corresponding the DC part here V capital out, and then that gives us the equivalent small signal transfer characteristic curve. So, to get that, you may say that the circuit wise what we are doing is this device, whenever we do have this device, we may simplify that circuit in terms of the small signal. So, the current here instead of capital I d s, we may say that this is small I d s as function of small g s. And we know that this function I d s, if you see I d s in terms of V g s, it is having a linear form, namely some factor here multiplied by V g s. So, that gives us, and the V g s is basically get to source voltage after dropping the DC part. So, this is what the equivalent circuit out of the transistor, and then of course, we do have the R d connected here. So, whatever the circuit we are obtaining by dropping the DC part is nothing but we can see another equivalent circuit, which is used for small signal transfer characteristic, and hence this equivalent circuit it is called small signal equivalent circuit. Okay. And whatever the total circuit, it is referred as small signal equivalent circuit, whereas this circuit it is referred as small signal model of the transistor. So, our next discussion it is the small signal equivalent circuit and small signal model of the transistor. So, whenever you are talking about the linearization is basically going towards that. So, let me take a short break, and then we will come back to discuss further about the small signal equivalent circuit.